Yeah, this is the third of the three cross-theme presentations. As you may have guessed from the place that we are in the program, this cross-theme is, whilst it of course spans all of the themes in the center, it's most closely related in terms of its working relationships between the components theme and the converters theme, which is where the presentation sits in the program. And so what I would like to do is to, once I've defined operational management and control, some of you may have some idea of what we're alluding to there, but I'll tell you specifically what we mean by it in the center in a few minutes. I want to look at the activity and the themes, and I'm going to concentrate really in terms of showing you actual technical work from the stuff that is coming out, particularly out of the converters theme. You've seen actually just in the presentation from Phil, and in fact from the other Phil's presentation this morning on devices, that there is clearly work going on to do with reliability in the components and the devices theme, and all of that is part of a set of information that has to pass up through a hierarchy all the way through to a converter to do this thing that we're calling operational management. I'm then going to look at one of these cross-theme projects that have been funded under the sort of general theme of operational management and control, and look at future work and some conclusions. So first of all, what do we mean by this as a title for a cross-theme topic? Well, the control aspect, of course, is something that, as power electronics people, we're all very well used to dealing with, where in terms of standard control, we think about controlling the input internal behavior and the output behavior of a converter, or perhaps a drive system, for instance. The aspects to do with the sort of regular functioning of a converter, as far as we're concerned in the center, the challenges there really occur when we start to go to high frequency, and we then have relatively small amounts of stored energy in a converter as our passive components shrink in size. And all of that leads us to needing higher and higher control bandwidths. So there's clearly a challenge as we go to higher frequency in terms of having the necessary high control bandwidth on our control system. The other challenge that comes about really is due to, on large converters, complex converters, particularly modular type grid scale converters, where you have a terrific number of devices and therefore a terrific number of gate drive signals, and also potentially a huge number of variables that you want to monitor and pass back into the control system. So there's just a sort of large size-based complexity issue with certain types of converters. So that's the sort of stuff you might understand typically by normal control of power electronics. In terms of operational management, then we're looking at adding to that and trying to improve the way that we operate converters, because we want to achieve the highest possible reliability. We want to take account of any redundancy that we have in the system, and to try and get to a point where we can operate a converter, as you can see here. We're trying to ensure high availability and scheduling of maintenance of a power electronic system using some form of fault diagnosis, or possibly action through redundancy in the system, or having some sort of controlled performance degradation. So really the question is, how do we take state of health type measurements from the underlying components in the converter and filter all of that back up into the way that we then run the control system for the converter, obviously taking into account the basic behavior that we must satisfy for the converter to operate properly, but then adding on this additional layer, trying to make sure that we operate all of the devices obviously within their bounds. And if you detect that a particular part of a converter is starting to degrade for some reason, and it depends obviously on the converter topology as to whether you can do anything about that, but if you've got some redundancy or modularity in the converter, you might be able to change the way that you operate the converter in order to get an additional life out of it, or at least run it in a controlled, degraded fashion. So you can see, I think, straight away why we therefore need to have input from all of the themes to make this type of system work. Because in order to do this thing here that we're calling operational management, where we basically then change our control strategy on the converter depending on the state of health of different parts of the subsystems of the converter, we need to know something. We need to somehow figure out state of health of components. We need to, at the same time, probably have some sort of lifetime model based on what we're doing and what our mission profile is going to be for the converter, in order to successfully operate some form of scheme that allows us to extend the life of the converter or run in a degraded mode, etc., etc. So you can see that it really is a full stack of requirements all the way through from the devices theme, which we talked about this morning in terms of looking at reliability and figuring out failure of devices, through into components, then actually implementing these sort of strategies at a level in the actual converter itself once you've got the information passed up from these lower two layers. And of course the same sort of thing in drives, sort of on the same plane really as converters in terms of needing information from these previous two layers. So I'm going to particularly talk about the types of activities that we've been doing in regards to modular type converters and what we've been doing here in regards to operational management. So I'm sure lots of you are familiar with these types of modular converters, but some of you may not be. So here is, this is a sort of system that you use for HVDC transmission, and you have a converter at each end of the DC cable, which is coming out here, and if you're exporting energy, obviously this is inverting, and if you are importing energy into the system, this converter here is rectifying. In order to get the high voltages, you build this out of a whole load of cells, and in most types of this type of converter, these cells are identical repeated cells. So inherently you have modularity in the system. This also then gives you inherently the ability to do some form of redundancy and duplicating tasks, if you like, between cells. So if a particular cell looks like it is somehow degrading, and that could be whatever particular part of that component cell that is starting to degrade, you might be able to shift the work that you would normally have done by that cell onto the other cells in order to then distribute the load across the parts that are still healthy. So clearly, in order to do that, you're going to need some basic input information about the state of health of the device, and that is then going to change the way that you actually then operate your control strategy for the converter. So I'm not going to say anything for the moment about actually figuring out the health of the actual module. I'll come back and talk about that a little bit at the end. But let's assume for the moment that we do have some information about the state of health of constituent parts of this converter, and we then want to change the way that we operate the converter to compensate for the fact that we know we've got some degradation. So this is a cell, this is a half-bridge cell from an HVDC converter. You can see the large cell capacitor there in blue. So a very basic thing that you can do, but shown here in simulation to be relatively effective, depending on the particular cell topology, sometimes you have a half bridge, sometimes you have a full bridge. Here with a full bridge cell topology, clearly you've got two possible current paths here giving you 0 voltage loops across this cell. You've got this one here and this one here. So if you detect that a particular device in one of those loops is overheating, then what you might want to do is simply change the way that you operate the 0 volt loops for that cell, and therefore run the current through the devices that are in better condition and are not heating up. So whatever the reason is for it heating up, if you detect that that's a problem, you can shift the current loaded onto different devices. And you can see a simulation of that here, where we've got something happens here maybe with the cooling of a particular device. And you can see the temperature starts to increase on a device. What happens then, that's measured by the control system that's running this converter, and the control system reacts by changing the duty cycle that we spend between this 0 volt loop and this 0 volt loop, and therefore you get basically a stabilization relatively quickly of the temperature in that device, and the trade-off is the other device here, are the other devices that are taking more current than they would previously on a 50% duty cycle starts to increase. But ultimately what you've done is you've stopped the thermal runaway of the device that was looking rather unhealthy. You can also play other sorts of tricks. So if we take the half-bridge converter, then what you tend to find when this type of converter is either exporting or importing real power is that the lower devices in the half-bridge, the low-side devices, will tend to heat up more than the high-side devices. And that's just simply because if you're mainly dealing with real power, of course, the peak of the current tends to happen at the point when these cells are not subtracting voltage from the DC link. And consequently, you end up with more 0 volts switched in, and therefore you get more current paths through the lower devices than the upper devices. And of course, then you get exactly the same on the lower side. If you're acting as a StatCom, then you get more equal power loss between the upper and the lower devices. But of course, most of the time you're not operating, at least you're not operating primarily as a StatCom with this type of device. You are exporting and importing real power. You then have some additional freedom to operate here. If you were to, for instance, add a small DC voltage offset, common mode across these three phases, you can change the particular arrangement of cells during the upper and lower cycles of current, so you can therefore effectively switch some power loss out of the top side and into the lower side of the system. So these are relatively small changes, but if you sort of add up all of these different degrees of freedom that you have with this type of converter, it may well be able to extend the ability of this device, this converter system, to operate. One of the other things you might want to do if you detect a particular device is starting to fail, and that could be a capacitor or it could be one of the semiconductors, is then to optimize the switching pattern and try and reduce the overall wear on that entire cell. Of course, in order to do that, you still have to maintain the things we were talking about earlier with the basic control of the system, where we're talking about internal states. Clearly, you still have to maintain energy balance on these individual cell capacitors. And so when you then look at the way that you try and offload work from this cell in order to try and let it cool down if it's overheating or you detect some wear, you have to take that into account. And this can be quite complicated on a large system. Actually figuring out what all the switching states will be in order to maintain that energy balance and to do what you want to do in terms of offloading the cell, it can be quite difficult to get a really optimal solution to that in real time. And you can see here several different algorithms that are being used in order to, on this side here we have optimality of switching as a function of something that's related to the number of cells with different algorithms, and some of these things will compute very quickly, but they will get a non-optimal answer, and the more complex solutions will take longer, but we'll get a more optimal solution for offloading that cell while maintaining proper operation of the converter and the capacitor voltages. Something that's a little bit more tentative that we've just been looking at recently is if you start to have a device failure and you don't get a device switching properly on or properly off, you can detect, this is something that's used in two-level converters, looking at voltages which are not reaching properly either zero or the cell voltage, and then you can maybe simplify the number of signals that you need as feedback to the control system to figure out that some of these devices are starting to fail. Because you could maybe do something relatively simple, like look at the overall voltage you expect to get across a bunch of cells and see whether that's equal to an integer number of cell voltages. And if it's not, then you must probably be dropping a lot of voltage across a particular device. And consequently, this is something that you might be able to use to react very quickly if you detect a device is starting to fail. Okay, I'd now like to move on and talk for a few minutes about the cross-theme funded project in this area, which is related to development of silicon carbide press pack modules. So the aim here is to demonstrate actually a real working prototype of silicon carbide dies put into a press pack type construction. So we're doing this with diodes and then later with MOSFETs. We're using some Cree devices, the bare dies that were available from Cree. Now, obviously the overall press pack construction is relatively well understood as a technique. I mean, obviously press pack devices have been available for a long time with silicon dies. What we're aiming to do here, therefore, is to use that well-known packaging style and look at optimizing it specifically for silicon carbide. And of course, then the things that you can optimize are things like the materials that you use for the contact pads and the pressure of those contact pads. And the way that we are tackling this problem is some work that has been led by Greenwich on finite element. Obviously, then we're producing a test device, and we're going to test this in some basic test cell. So this work is led by Warwick, and then contributing Greenwich, Imperial and Nottingham. So here's a drawing of what the overall test device is going to look like. You can see here the actual press pack cell with, there's a die sitting in here, connected between these two heat sinks. A bit more of detail here. One of the things that we're interested in doing in particular, and of course this is all to do with increasing reliability of the device and figuring out how the device is going to behave over a longer period, so that it can then, if we start to use this sort of device in a large-scale converter, we can feed that information all the way up into the control system for the converter in order to do this overall operational management type control scheme. So you can see here what we're interested in doing particularly is optimizing these interfaces here and choosing the anode and cathode contact to be of a material which is the best possible material we can put into here, and also optimizing the pressure in this stack, taking account of stress and obviously thermal and electrical resistance. So a whole bunch of parts that we've got. A lot of this actually now is actually with us. And so it's been ordered and it's already been manufactured. We are looking at, in particular, two different contact materials. We're looking at molybdenum and aluminium graphite as the two different sorts of cathode contacts. And we're starting then to look at what happens here with a single diode. Later on, we will start to look at tiling multiple dies together and to make a larger press pack module. We're starting with one, and we're later as well going to look at MOSFETs. But some of the work that we started doing is this FEA type work led by Greenwich, looking at this the contact and the contact material. And here's some early results from this project. And you can see here that the contact material has very little effect on the temperature at the junction between these materials and in the silicon carbide die, but the stress distribution is slightly different as a function of current here, depending on the particular type of contact material that's being used. So it looks here, for instance, the lower stress comes with the aluminium graphite, and therefore that may be a better solution, but it's not absolutely necessarily the case. I guess we need to look at other factors here, but I guess a first cut of this says that the aluminium graphite maybe is the better solution for the contact material. Looking to extend the work then into putting multiple devices in parallel, and to move on also to looking at a MOSFET module as well as the diode module. So what are the things that we also would like to work on as part of operational management and control? I think one of the things that clearly is absolutely critical to being able to achieve this sort of health management within a power converter and understanding the health of the devices clearly is to do some form of measurement and modeling of the behavior of the devices. And I mentioned at the beginning we would come back to this. So we have a whole bunch of ideas and some results about the sort of things we can do at the converter level, assuming we understand something about the state of health of the devices. Now we need to look at what we can actually do in order to figure out the state of health of the devices. So one of the things that we're planning on doing, for instance, is doing some maybe some time domain reflectometry techniques that is kind of bringing RF type techniques into power electronics, where we can start determining parameters in the device. We can see things like bond wire liftoff. We can maybe measure changes in device capacitance, for instance. And here's a sort of circuit that you might be able to use to do that. One of the difficulties of doing this sort of measurement is that this is exactly the sort of measurement that you could do in a laboratory environment with a VNA, for instance, 20,000 pounds of lab equipment. And you could get real results, and you can see changes in the device as you get bond wire liftoff. You can get all of that information out of an expensive piece of lab equipment. The challenge here, and this links very well into the work that you just heard described by Phil in the components theme to do with gate drives, is how do you take this sort of system and integrate it into a gate drive in such a way that it's going to be cost effective. So ultimately, what we are effectively wanting to do here, you can see the way that this is configured in terms of information flow between the themes, where we are trying to do this operational management and control in the converters theme, fed up with information from the components theme, which in turn has information fed in through the devices theme about the state of health of devices. So we want to ultimately show significant improvement in availability of power electronics through the use of fault diagnosis and preventative maintenance. We'd like to, for the types of converter that are amenable to it, then use that information to provide graceful degradation of, in particular, modular type converters, which should lead to a significant reduction in the cost of outages. Thank you.